Usually when we talk about a construction site, there's this expectation of like old school grit and paper.
Oh, absolutely.
You picture a massive table in a dusty, unair-conditioned trailer covered in these giant, unrolled blueprints.
Right, the classic image.
Yeah. You imagine a project manager with a hard hat just pointing a calloused finger at a flat line drawing and saying, build it right there.
It's a very traditional, almost romantic image, really. A team of people pointing at two-dimensional lines on a flat piece of paper, using their collective imagination to somehow envision a complex, three-dimensional skyscraper.
And then just walking out into the mud to make it happen.
Exactly.
Right. But when you step into the actual reality of modern mega-scale construction today, that dusty trailer with the paper blueprints is, well, practically a museum exhibit.
It really is.
We are looking at an industry landscape that has entirely shifted from those flat drawings to massive, data-rich digital rehearsals.
It is the absolute definition of a paradigm shift. What we're really talking about today is the concept of building an entire multi-million-dollar project twice.
Twice?
Yeah, you build it once perfectly in pixels, and then you build it once in reality.
Okay, let's unpack this, because framing it as just 3D drawing completely misses the mark.
Oh, entirely.
And to really understand how this works, we are going to dive into a specific document today. It's the BIM Essential Guide for Contractors.
Right.
This was published by Singapore's Building and Construction Authority, the BCA. And our mission for this deep dive is to demystify building information modeling, which is what BIM stands for.
Yes.
And we want to see how it completely rewires the way we construct the world around us. So if you're someone who looks up at those massive tower cranes in your city and wonders how it all comes together without collapsing into absolute chaos, well, this is for you.
It's a great foundational text for exactly that.
We're getting into how this technology transforms the entire construction value chain.
And, the BCA put this guide together specifically to prove a point. For a long time, people thought BIM was just a fancy 3D visualization tool for architects to show off their designs to clients.
Like a pretty render.
Exactly, just pretty pictures. But the BCA wanted to show that it is actually a foundational, game-changing technology for contractors.
Right.
It dictates everything from initial feasibility and cost tracking all the way to how a facility manager runs the building decades down the line.
It is a hyper-detailed digital clone of a building.
Yeah.
And the journey of this digital clone really starts long before a single shovel hits the dirt.
Yes, it starts at the very beginning.
It starts with the pitch, the tender stage. Because before a contractor gets to build anything, they actually have to win the job.
That's the hard part.
Right. They have to figure out exactly what it's going to cost.
Precisely. At this bidding stage, the client or the consultants might hand over their preliminary BIM models to the competing contractors.
Okay.
These come in various file formats. So the guide mentions DWF, 3D, PDF, IFC, or native files.
Which sounds like alphabet soup.
It does, but think of those just as different digital translation tools that allow various software programs to read the 3D data.
Makes sense.
So the contractor can use those files, or they can build their own BIM model from the traditional 2D drawings. But the primary goal here is cost estimation.
Right, and if we think about the old way of estimating costs, a quantity surveyor would sit at a desk with a physical scale ruler.
Yep, doing it all by hand.
They would measure lines on a piece of paper, manually counting every single door, window, and square meter of drywall.
It sounds exhausting just talking about it.
It really does. It's like pushing a cart through a massive grocery store and having to manually write down the price and barcode of every single item on a notepad to figure out your total before you even get in line for the register.
A highly manual, highly error-prone process.
Yeah.
But with BIM, the software looks at the 3D model and instantly generates a schedule of objects linked to an external cost database.
Oh, wow.
It functions much more like scanning that barcode at checkout.
That's incredible.
The system instantly reads that there are, say, exactly 40 bifold doors and 12 single flush doors, and it pulls the current market pricing for each.
But wait, if the computer's doing the counting, the math is only as good as the model, right?
Well, yes.
Like, what if a digital wall is drawn weirdly, say the architect measured from the center line of the wall instead of the outside edge? That would completely change the calculated square footage.
It absolutely would.
The computer wouldn't inherently know the architect's intent, right?
Yeah.
It would just spit out a bad number, which could cost a bidding contractor millions.
You've hit on a crucial nuance here, which is why rigorous quality assurance is mandatory. The modeling methods directly impact the physical quantities.
Right.
The guide highlights a great example regarding foundations, specifically piles and pile caps.
Okay, so a pile is the deep concrete pillar driven into the earth, and the pile cap is the thick concrete block sitting on top of it that actually supports the building's weight.
Right. So if a lazy digital modeler just draws a single, solid, continuous block for both the pile and the cap.
The computer just calculates one giant volume of concrete.
Exactly.
But
In reality, pouring a pile cap requires a specific amount of wooden formwork.
like a temporary wooden mold.
Yes, to hold the wet concrete in place while it dries. If the modeler draws the pile and the pile cap as two separate, distinct elements, the BIM software can calculate the exact surface area of the pile cap.
Oh, I see.
And then it automatically determines exactly how much wooden formwork the contractor needs to buy.
So the digital model literally has to be built with the physical construction sequence in mind.
It's essential.
The contractor's checking the model not for how pretty it is, but for how it translates to real-world assembly. The guide mentions they can use built-in tools, like the warnings function in software like Revit, to catch these inconsistencies early.
Yes, catching a modeling error digitally costs a few clicks. Missing it could mean ordering 10,000 square feet of expensive formwork that you don't actually need, blowing up your bid, and losing the job.
Wow. So let's say they get the cost dialed in, and they win the bid. The guide then pivots to site and logistics planning, which I found fascinating.
It's a huge part of the process.
Because they aren't just modeling the permanent building, they're modeling the temporary ecosystem around it. The hoardings along the boundary, the entry gates, internal roads for trucks, site offices, storage zones.
It is vital to model the temporary structures, particularly on tight urban sites. And a key part of this is modeling the mobile vehicles and, most importantly, the tower cranes.
Right, the cranes.
They don't just place a static stick figure crane on the digital site. They model the exact mathematically precise swing circumferences of the crane arms.
They're digitally rehearsing the physics of the machinery. I imagine that's crucial because a crane operator isn't just swinging an empty hook.
Got it all?
They have a massive heavy load, wind resistance, and a counterweight swinging out the back. You have to ensure strict safety distances are maintained between that crane crank and any public infrastructure, right?
Exactly.
You can't have a steel I-beam accidentally swinging over an active highway.
That is the exact risk they are mitigating. And this naturally leads into another layer of logistics, which is 4D simulation.
4D, so that's adding time to the 3D model.
Yes. By linking the 3D model to the project's real-world schedule, you can animate the entire construction sequence day by day.
Oh, that's cool.
And this completely changes supply chain logistics.
Yeah.
Think about building a skyscraper in downtown Singapore. You do not have an acre of empty grass to just dump 500 tons of steel and let it sit there for a month.
So you have to orchestrate just-in-time delivery.
Precisely. The 4D simulation visually communicates to the entire site crew that, say, on Tuesday at 2:00 p.m., a specific truck needs to arrive, navigate the temporary internal road to a specific drop zone so the crane can immediately hoist a specific set of beams into an active zone.
That level of coordination is wild.
It prevents catastrophic logistical clashes, too, like realizing you were scheduled to dig a massive trench for new utilities on the exact same day you needed that space for a concrete truck to park.
Yeah, that would be a nightmare. Speaking of avoiding disasters, once the logistics are locked, the contractor gets bombarded with models from all the different consultants.
Oh, yes. The model dump.
Right. The architects, the structural engineers, the mechanical, electrical, and plumbing teams, the MEP guys. This moves us into the pre-construction stage. And historically, this seems to be where projects would just devolve into absolute chaos.
Chaos is a very good word for it. In the old 2D paper world, everyone designed in their own separate silos.
Right.
The structural engineer would draft a massive load-bearing steel beam on their blueprint. Completely independently, the mechanical engineer would draft a primary air conditioning duct on their blueprint, running right through the exact same spatial coordinates.
And nobody realizes the mistake until a guy is physically standing on a ladder 6 months later, holding a massive metal duct, staring at a steel beam that is entirely in his way.
And at that point, work just stops. RFIs, requests for information, are filed. Engineers have to frantically redesign on the fly.
Which sounds expensive.
Very. Materials are wasted and time is lost. So in pre-construction today, the very first step is merging all these discipline-specific models into a project review software.
And they have to establish a common coordinate system. Because if the architectural model assumes ground level is at 0 elevation and the structural model was drawn assuming ground level is at an elevation of 100 feet.
You merge them and the building looks like it's been torn in half.
Exactly. So you calibrate the coordinates so every model aligns perfectly in the digital space.
Right. Then you begin the primary objective of this phase, which is reviewing the building elements, particularly the mechanical and electrical penetrations that might compromise the structural integrity.
Here's where it gets really interesting. The visual strategy they use for this is what really shifted my perspective on how powerful this tool is. You have millions of complex components overlapping.
It's a lot of data.
To make sense of it, the guide outlines a very specific color coding matrix. Architecture becomes a dark green with a 30% transparency. Structure is dark brown. The ACMV, the air conditioning and mechanical ventilation, is light blue.
Very helpful for visually separating things.
Yeah. Plumbing is light green. Fire protection is light red. Electrical is purple.
It creates a highly readable environment. By making the architecture semi-transparent green, the contractor can effectively peer through the digital walls and floors to see the intricate, color-coded vascular system of the building beneath.
It's exactly like looking at a medical X-ray. You isolate the bones from the arteries. If you're zooming through this digital space and you see a light blue mechanical artery smashing directly into a dark brown structural bone, well, you have a massive problem.
We call those intersections clashes, and finding them is the primary reason this digital rehearsal exists.
Catching it early.
Yes, catching a clash in pixels costs nothing. Catching it in concrete is a disaster.
But wait, if I'm picturing $1 billion high-rise, there have to be tens of millions of overlapping components. Does the computer just scream with an error every time two digital pipes touch?
It certainly can.
I'd imagine you'd have to tell the software to ignore certain things, otherwise the sheer volume of data would be completely useless to a human being. How do you not get overwhelmed by thousands of errors?
What's fascinating here is that this is a major hurdle for teams transitioning to BIM. If you just hit the run button on an automated clash detection tool, the software will spit out tens of thousands of clashes.
Just a wall of red flags.
Exactly. Two pieces of drywall overlapping by 1 millimeter. Clash. A half-inch electrical wire passing through a standard wall. Clash. It's overwhelming. So contractors establish what we call clash rules to filter out the noise.
Okay, so a rule would essentially tell the software, ignore any clashes between pipes smaller than 50 millimeters and non-load-bearing architectural walls. Because you know the guys on site can just take a drill and easily punch a small hole through standard drywall without compromising the building.
Exactly. You intentionally ignore the minor, easily solvable intersections so the engineering team can focus on the catastrophic structural issues. You group these major issues by trade and prioritize resolving them.
The guide gives some really terrifying examples of what they uncover.
Oh, they definitely do.
Like a major cable support tray clashing directly into a concrete structural column. Lighting fixtures routed straight through cable supports. Or, my absolute favorite, discovering that an air conditioning duct was routed so low that the headroom clearance in a hallway dropped to 1,800 millimeters.
Which is less than 6 feet of clearance.
Imagine finishing a multi-million-dollar commercial build and suddenly realizing that anyone over 5'10" has to physically duck to walk down the main corridor.
That is the kind of real-world embarrassment and financial liability that a well-coordinated digital model prevents.
So all of these clashes are identified, grouped, and resolved digitally. The engineers reroute the light blue duct around the dark brown beam. The digital world is now pristine, heavily coordinated, and mathematically perfect.
In theory, yes.
But then we have to move into the execution phase, the construction stage. How does this pristine, pixelated utopia actually survive the muddy, chaotic reality of a physical site?
Well, the digital model doesn't just sit in an office. It becomes the active tool for managing that site chaos. When physical discrepancies inevitably pop up, the contractor uses the 3D construction model to raise their RFIs directly to the consultants.
The guide has some excellent visual examples here. Instead of trying to describe a problem over the phone, they send a 3D screenshot showing an entire section of architectural windows inexplicably missing from the structural model.
It's much clearer that way.
Or a structural review highlighting that the architectural facade columns were modeled significantly smaller than the actual load-bearing concrete columns need to be.
And because they are communicating in 3 dimensions, contractors can move beyond just asking questions. They can proactively propose visual solutions for constructability. For instance, the guide highlights a scenario where a contractor proposes omitting a corbel beam. A corbel beam is essentially a piece of concrete that juts out from a wall to support a heavy weight.
Okay.
The contractor realized that physically pouring that specific shape on site was going to be needlessly difficult.
Hmm.
So they manipulated the 3D model, shifted a main beam to take the load instead, deleted the corbel, and sent the updated 3D view to the engineer for approval.
It's highly collaborative.
Mm.
They are providing a fully visualized, mathematically sound alternative.
Exactly.
And that brings us to how the workers actually physically building this get their instructions. We see a massive evolution in shop drawings.
Yes, shop drawings are the highly granular, micro-level instructions used by fabricators and builders for specific components. Historically, these were entirely 2D drafted lines.
Right.
But now projects are transitioning. Some use a 2D plus 3D approach, where the official sign-off is on a 2D document, but everyone uses the accompanying 3D model to actually understand the spatial reality.
Makes sense to have both.
For extremely complex geometries, like a curved museum roof, projects are moving to pure 3D review, where the model itself is the legally approved document.
But the guide also details a hybrid approach. This is where they generate a 2D view directly from the 3D BIM model, but then draft traditional 2D line work over it to show hyper-specific joint details.
Yes, the hybrid approach is very common.
For example, detailing the exact layers of an EPDM membrane, which is essentially a heavy-duty, weatherproof rubber sheet used on flat roofs.
It's about choosing the right tool for the job. You use the 3D model for complex spatial coordination, but a simple 2D drafted line might still be the most efficient way to communicate a 2mm layer of waterproofing to the roofing team.
That makes perfect sense.
Right.
But here is the ultimate pragmatic question.
Okay, let's hear it.
So the model is perfect, the shop drawings are approved, but how do the guys actually pouring the concrete on a muddy Tuesday morning use this 3D data? How do they take this incredibly dense 3D data and use it to pour a concrete footer in the exact right spot on planet Earth?
If we connect this to the bigger picture, this specific moment is where the digital world physically touches the real world. We use field survey set-out tools.
Field survey set-out tools.
Right. The contractor takes the coordinated BIM model and extracts the precise X, Y, and Z digital coordinate points for, say, a curved row of structural columns.
Okay.
They export those digital coordinates directly into physical surveying equipment on the site, specifically a piece of technology called a robotic total station.
So instead of guys out there with tape measures and string lines doing manual trigonometry, the physical surveying equipment reads the 3D computer model.
Yes. The robotic total station sits on a tripod, reads the digital coordinates, and uses automated lasers to physically point to the exact millimeter-accurate location on the dirt or the concrete slab where that specific column needs to be cast.
That is wild.
It completely bridges the gap between the screen and the site, eliminating the human error of someone misreading a tape measure or pulling a string line at the slightly wrong angle.
That is wild to visualize. They are literally projecting the digital matrix onto the physical dirt. And because this technology allows for such insane real-world precision, it unlocks a massive shift in how we build, which is moving construction off the site entirely.
Prefabrication. It is truly the holy grail of modern construction productivity.
Yeah.
Think about it. If you know with absolute millimeter certainty that a designated space on the 14th floor will be perfectly clear of structural beams and plumbing pipes, you no longer have to build an intricate air conditioning duct on site in the rain, surrounded by dust and competing trades.
You just have the spatial certainty to build it in a climate-controlled factory.
Exactly.
And BIM is the engine that drives that spatial certainty. The guide notes that contractors can use the model scheduling data to instantly identify repetitive elements.
Like doors or windows.
Yeah, the software can filter the data and say there are 40 identical bifold doors and 60 standard double flush doors in this project. It makes total economic sense to just prefabricate all of them.
But it goes far beyond standard doors. By analyzing that fully clash-detected model, contractors can isolate massive complex assemblies for prefabrication. We're talking entire structural walls, precast concrete stairs, and highly intricate mechanical assemblies.
Shipping them in.
Yeah, they build a massive plumbing manifold in a pristine factory environment, ensure the quality's perfect, put it on a truck, crane it into the building, and it bolts into place perfectly on the first try because the digital model guaranteed the space was clear.
So the building goes up faster, safer, and cleaner. So what does this all mean for the end of the project?
The handover phase.
Right. What happens when the building is finished? The crane comes down, the ribbon is cut, the client moves in, and the contractor goes home. Does this massive, beautiful, highly coordinated 3D model just sit on a hard drive somewhere gathering digital dust?
That would be a monumental waste of valuable data. At the end of the project, the contractor produces what is called the as-built model.
The as-built model.
This is the final digital clone, updated to reflect exactly how the building was actually constructed, incorporating any minor on-site deviations. And this as-built model transitions into a vital facility management tool for the operations and maintenance team.
The O&M team. So the digital twin actually becomes the literal operating manual for the physical building.
Exactly. But for it to be useful, the O&M team needs specific data front-loaded into the digital objects. It's no longer just about geometry and clash detection. The model becomes a living database.
The guide has a detailed table on this, and it shifts from just visual data to deep operational data. The contractor isn't just handing over a digital box-labeled door.
No, it's much more detailed.
They have to input the specific fire rating, say, confirming it's a 2-hour fire-resistant door, directly into the element's digital properties.
Think about the economics of this for a facility manager. Over a 50-year lifespan, maintaining a building often costs more than building it.
That's a huge point.
If you click on a digital fire extinguisher in the handover model, it doesn't just show you where it's hanging. The contractor has embedded the specific type, the supplier name, and the exact expiry date.
Which fundamentally changes maintenance. 5 years down the line, a facility manager doesn't have to walk all 40 floors with a clipboard checking physical tags.
Exactly.
They just sit at their iPad, run a search in the BIM model for fire extinguishers expiring this month, and the digital twin instantly highlights exactly which extinguishers on which floors need to be replaced.
It creates incredible efficiency. They track breakout glass locations for safety. For major mechanical equipment like fire pumps or massive HVAC chillers, the model holds the exact pump capacity, the serial number, and the warranty information.
So if a chiller breaks down on the roof in the middle of a heat wave, the maintenance team doesn't have to go gigging through a basement filing cabinet looking for a paper manual from 3 years ago.
Nobody wants to do that.
Right. They click the broken chiller in the 3D model, pull the supplier name, realize it's still under warranty, and dispatch the exact replacement part before they even step foot in an elevator.
That front-loaded data saves millions in operational costs. It creates a living, breathing digital twin that continuously adds value long after the construction crew has left.
Okay, let's synthesize this whole journey, because it is a massive amount of technical ground to cover.
It really is.
We started with the misconception that BIM is just architecturally pretty 3D drafting. But by digging into this essential guide for contractors, we see that it is actually the central nervous system of modern building.
Absolutely.
It is an automated cost estimator that knows exactly how much wood you need to mold a concrete foundation. It's a physics simulator analyzing tower crane swing risks before the crane even arrives on site.
It does it all.
It's an X-ray machine using complex clash rules to stop mechanical ducts from smashing into structural columns. It's a translation tool exporting digital coordinates directly into robotic lasers to pour concrete with millimeter perfection.
Such a huge leap in technology.
And finally, it evolves into a hyper-detailed facility management database that tracks the expiry date of a single fire extinguisher on the 12th floor. It is, from start to finish, the ultimate digital dress rehearsal.
It really is. The level of coordination, foresight, and data integration required is entirely unprecedented in the history of humans building things.
So the takeaway here for you listening, the next time you walk past a construction site or the next time you step into the towering lobby of a massive new high-rise, take a second to look at the walls. Look up at the ceiling.
Yeah, take it all in.
Because you aren't just walking through a physical structure. You are walking through a physical printout of a meticulously coordinated data matrix.
And this raises an incredible concept, a final thought for you to really mull over. Okay. If a single physical building requires this fully coordinated digital twin, where every single duct is clash detected and every fire extinguisher's expiry date is tracked to ensure safety and efficiency, what happens in the near future when this level of data-rich modeling is applied to entire cities?
Oh, wow.
Imagine urban planners and governments using city-scale BIM to digitally rehearse the traffic patterns, the underground utilities, the energy grid, and the mass transit infrastructure of a metropolis, optimizing the whole system before a single brick is ever laid.
A digital rehearsal for an entire metropolis. We have definitely come a long, long way from a dusty trailer, pointing at a piece of paper and saying, build it right there.
Thanks for joining us on this deep dive. We'll catch you on the next one.